Okay, so we're going to work a specific example now of using Coulomb's law to calculate the electric field at a particular point in space. We notice that we have three charges here. We have Q1, which is 2 microcoulombs, Q2, which is also 2 microcoulombs, and Q3, which is -4, it's a negative charge, -4 microcoulombs. And what we wish to do is calculate the electric field here at this location, which is 40 centimeters away from the Q3. And we're going to have to figure out how far away it is from Q1 and Q2. We are given that it's 30 centimeters or 0.3 meters, that these are displaced here from my origin. And so actually, if we notice here, we can actually immediately see that the distance, which we're going to need here as we calculate the electric field from each of these contributions, is actually going to be this positive charge here to here. This distance is going to be, it's a 3, 4, 5 triangle. So the distance from here to here, I could say as, for example, R2 is in the absolute value of that, is going to be equal to 0.5 meters because this is a 3, 4, and 5 triangle. So similarly over here, I can say the same thing, that this is R1 absolute value, and that's the vector connecting this Q1 here, and its magnitude is equal to 0.5 meters. So great, so I think we have a good setup here. We can actually sort of start to guess what the electric field is going to look like at this point here by saying, okay, if I had this and this, I noticed that one of these charges has kind of a contribution along this line here pointing up, and the other one has, if I could draw a straight line, this has an electric field pointed in this direction here. And if you notice something, actually, one has a component that's kind of pointing out and up, and this one has out and down. So actually, we already can notice that these two are going to have, basically, we're only going to want to capture the sort of x-hat component because of these partial cancellations here. So in other words, if we wanted to think of it as kind of that there's some angle alpha here, we really only want to take the cosine of that alpha. So if you remember that this angle here is actually the same as this angle here, we could actually just write down directly that the cosine of this angle is equal to the adjacent over the hypotenuse. Just as a reminder that cosine of an angle, right, is equal to the adjacent length divided by the hypotenuse length. So there's some mnemonics out there for remembering these things, but I won't go over that right now. So we are going to take the cosine of alpha, which in this case is going to be 0.4, the adjacent, divided by the hypotenuse, which is 0.5. And we're going to do that for actually both of those as we pick out the x-hat component of each of these contributions here. So so the electric field total that we wish to calculate is the electric field from the first, electric field from the second charge, and the electric field from the third charge. And we're going to calculate each of those terms. And if I notice here, I'm just going to be applying Coulomb's law. So for example, for the first electric field, I'm going to notice that the distance is this 0.5, that the charge is this 2 microcoulombs, and I'm going to actually just write down symbolically first, then we'll plug in the numbers on the next step. So I'll have K times Q1 divided by R1 squared. And as mentioned, I'm only going to pick out the x-hat component of this, so I'm going to write the cosine of alpha here in the x-hat direction. Similarly, for E2, I'm going to write KQ2 over R2 squared, and this is also going to be a cosine of this alpha, where this cosine of alpha is equal to 0.4 over 0.5. Finally, I'm going to add the contribution from Q3. And again, this is just going to be the same exact scenario here, where I have a K Q3 over R3 squared. And it looks like R3 is the distance from this minus charge to the point I'm interested in over here, which is 0.4. And this also is in the x-hat direction. You might be thinking, but wait, hey, isn't the contribution from this minus charge going to give me an electric field in the minus x-hat direction? And it definitely will. Right now, I'm just following the rules, whatever this says, and one of the things that comes out is that by putting a minus Q3 into this equation here, we're actually going to find that we end up getting a contribution in the minus x hat direction. So let's go ahead and plug in some numbers. We notice that we have a k in common for all of these here. So that's 9 times 10 to the 9 newtons times meters squared per Coulomb squared. So that's my k. I also noticed that my Q1 and Q2 are the same, and my R1 and R2 are the same, and my cosines are the same. So basically, I'm going to just get twice this term here. So to combine my E1 and E2 terms, I will pick that I'm going to do twice this value here, which is going to be 2 times 10 to the minus 6 coulombs, divided by this distance here, right, which is the same distance here, 0.5 meters squared. And so I'm going to be squaring this value here. And so that takes care of my E1 and my E2 terms. Oh, I almost forgot the cosine term. And that's going to give me a 0.4 over 0.5. So it's a small correction, but it's an important factor here in being able to really make the full calculation. And this will be in the x hat direction. And then this part here, if I consider that, let's see here, I'm going to just kind of change my parentheses here just a little bit here so that I can say that all of this here can include this term here, since we have a k that's in common with all these. And I'll write down that we have a minus 4 microcoulomb here. And this is going to be divided by 0.4 meters squared. Okay. So finally, we can put together all of our numbers here, and we will calculate our result. Okay, so I got out my calculator and I plugged in these numbers. So if you remember, this first term here was a result of these first two terms, E1 and E2. And that calculated the composite of the addition of these two vectors here is one resultant vector of about 115,000 newtons per Coulomb in the positive x hat direction. Now, when I calculated the contributing electric field term from the minus 4 microcoulomb term, I actually got 225,000 newtons per Coulomb in the minus x hat direction. So actually, the result ended up overall being minus. So in fact, the fact that this charge here is the same as these two charges combined, but the distance is closer, actually means that the electric field contribution from these first two might have been in, let's say, this far, but the electric field contribution because of this minus charge is a little bit longer. So you have one that's longer than the other, so we end up getting an overall electric field in the minus x hat direction. So we have about 110,000 newtons per Coulomb. And let's say, for example, that I put or even that there was a charge flying by here. Let's say it had 2 microcoulombs, right? So there was if I put here some charge, let's call it, I don't know, sometimes people call this as a test charge, but I could say a Q is equal to 2 microcoulombs here. Then the force on that charge, force on Q, would be equal to the electric field total at that point times Q. So then I would end up with basically this, let's just approximate it here as 110,000 times 2 microcoulomb. So we'd keep in mind here the units here is newtons per Coulomb. The units here are coulombs. So we're going to end up with a result in newtons. And just going off my notes here, this total force is then going to be equal to, and this is going to be x hat direction here. This total force will be minus 0.22 newtons in the x hat direction. Or if you'd rather, we can actually write it as 0.22 newtons in the minus x hat direction. So if we had a positive charge here, then it would feel a force going in the minus x hat direction. What if we put a negative charge there? That's right, it would be in the positive x hat direction. So anyway, so we've calculated now a force in newtons for a particular charge, and we got there by calculating the total electric field contribution from a series of calculating the electric field from each charge individually. You can often look for symmetries that help you to solve a problem, but even if those are not available for a given problem, you can always go back to the original definition of how you compute the electric field contribution from each charge. And the key word is that they superpose, that there's a superposition between these fields. So you see how we wrote here this electric field 1 plus electric field 2 plus electric field 3 and so on. We can write this in a sum notation as summing over all the charges of KQI over RI squared, in the RI hat direction. So this would actually compose basically, if you wanted to figure out the total electric field, you could just add up the contribution from each of those charges individually, and you'd have the electric field at any point that you're interested in space. Thank you.